Hello, and welcome. In this video, we will explore the fundamental concepts of indefinite integration, a core topic in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to define and calculate indefinite integrals, understand the significance of the constant of integration, and apply key integration rules to solve a variety of problems. Integration is often described as the reverse process of differentiation. If we know the derivative of a function, we can work backward to find the original function. This process is called anti-differentiation or indefinite integration. Let's consider a simple example. We know that the derivative of x cubed is 3x squared. This means that x cubed is an antiderivative of 3x squared. However, x cubed is not the only function whose derivative is 3x squared. What about x cubed plus 5? Its derivative is also 3x squared. The same is true for x cubed minus 10. In fact, the derivative of x cubed plus any constant, which we'll call c, is 3x squared. This constant c can be any real number. This leads us to the formal definition of an indefinite integral. If the derivative of a function f of x is equal to a function f of x, then the indefinite integral of f of x with respect to x is f of x plus c. The symbol we use is the integral sign, which looks like a stretched s. Here, f of x is called the integrand, indicates that we are integrating with respect to the variable x, and c is the constant of integration. This constant represents the entire family of functions that have f of x as their derivative. So, to recap, finding an indefinite integral means finding a function whose derivative is the given integrand, and we must always remember to add the constant of integration, c. Now that we understand the basic concept, let's look at some fundamental rules that make integration more manageable. These rules are direct consequences of the corresponding differentiation rules. First, the constant multiple rule. This rule states that any constant factor within an integral can be moved outside the integral sign. This is very useful for simplifying expressions. Let's quickly prove this. Suppose f prime of x equals f of x. We know from differentiation that the derivative of k times f of x is k times f prime of x, which is k times f of x. Therefore, the integral of k times f of x is k times f of x plus c. Since f of x is the integral of f of x, we can write this as k times the integral of f of x plus c. This confirms the rule. Second, the sum and difference rule. This rule allows us to integrate a sum or difference of functions term by term. This is incredibly powerful as it breaks down complex integrals into simpler ones. The proof is similar. If f prime of x equals f of x and g prime of x equals g of x, then the derivative of f of x plus g of x is f of x plus g of x. Integrating both sides gives us the rule. So, to summarize, we can pull constants out of integrals, and we can integrate sums and differences one term at a time. These two rules are the foundation for integrating polynomials and other combinations of functions. Now, let's build a table of basic integrals. We can derive these by reversing the differentiation rules we already know. First, the power rule. We know the derivative of x to the power of n plus 1 is n plus 1 times x to the power of n. Reversing this, the integral of x to the power of n is x to the power of n plus 1, all divided by n plus 1 plus c. This rule is valid for any real number n, except for n equals negative 1. Why is n equals negative 1 excluded? Because it would lead to division by 0. We'll address the case of n equals negative 1, which is 1 over x, in a moment. Next, the integral of a constant. The derivative of x is k. Therefore, the integral of a constant k is kx plus c. For exponential functions, the derivative of e to the x is e to the x. So the integral of e to the x is also e to the x plus c. Now for the special case of n equals negative 1. The derivative of the natural logarithm of the absolute value of x is 1 over x. Therefore, the integral of 1 over x is the natural logarithm of the absolute value of x plus c. The absolute value is crucial because the logarithm is only defined for positive numbers, but 1 over x is defined for both positive and negative x. Let's quickly recap these essential rules. The power rule for x to the n, the constant rule, the exponential rule for e to the x, and the logarithm rule for 1 over x. These are the building blocks for many integration problems. Let's put these rules into practice with a few examples. Our goal is to find the indefinite integral of a polynomial. Consider the integral of negative 2x cubed plus 5x minus 2 with respect to x. First, we can use the sum and difference rule to integrate each term separately. This gives us the integral of negative 2x cubed plus the integral of 5x minus the integral of 2. Next, we use the constant multiple rule to pull the constants out of each integral. This simplifies to negative 2 times the integral of x cubed plus 5 times the integral of x minus 2 times the integral of 1. Now we apply the power rule to the first two terms and the constant rule to the third term. The integral of x cubed is x to the power of 4 over 4. The integral of x, which is x to the power of 1, is x squared over 2. And the integral of 1 is x. Don't forget the constant of integration, c. Finally, we simplify the expression. Our final answer is negative 1/2 x to the fourth plus 5/2 x squared minus 2x plus c. A great way to check your work is to differentiate your answer. If you differentiate negative 1/2 x to the fourth plus 5/2 x squared minus 2x plus c, you should get back the original integrand, negative 2x cubed plus 5x minus 2. Let's try another example, this time involving exponential and power functions. We want to find the integral of 5e to the x plus 2 over the square root of x. First, let's rewrite the second term using exponent notation to make it easier to apply the power rule. The square root of x is x to the 1/2 power. So 2 over the square root of x is 2 times x to the negative 1/2 power. Now we can integrate term by term. The integral of 5e to the x is 5 times the integral of e to the x. The integral of 2x to the negative 1/2 is 2 times the integral of x to the negative 1/2. We apply the exponential rule to the first term and the power rule to the second term. The integral of e to the x is e to the x. For the second term, we add 1 to the exponent negative 1/2, which gives us 1/2. Then we divide by the new exponent 1/2. Now, let's simplify the expression. Dividing by 1/2 is the same as multiplying by 2. So we have 5e to the x plus 2 times x to the 1/2 plus c. This simplifies to 5e to the x plus 4 times the square root of x plus c. Again, you can differentiate this result to verify it is correct. Let's expand our toolkit to include trigonometric functions. Just like before, we can find their integrals by reversing their derivatives. We know the derivative of sine x is cosine x. Therefore, the integral of cosine x is sine x plus c. The derivative of cosine x is negative sine x. This means the integral of negative sine x is cosine x plus c. If we want the integral of positive sine x, we can multiply both sides by negative 1, giving us negative cosine x plus c. The derivative of tangent x is secant squared x. So the integral of secant squared x is tangent x plus c. These three are the most common trigonometric integrals you'll encounter. There are others, like the integrals of secant x tangent x and cosecant squared x, which you can find by reversing the derivatives of secant x and cotangent x, respectively. Let's do an example. Find the integral of 2 sine x minus cosine x. Using the sum and difference rule, we can integrate term by term. This becomes 2 times the integral of sine x minus the integral of cosine x. Now we apply our new trigonometric integral rules. The integral of sine x is negative cosine x. The integral of cosine x is sine x. So we have 2 times negative cosine x minus sine x plus c. Simplifying, our final answer is negative 2 cosine x minus sine x plus c. Now let's tackle a more complex problem that requires some algebraic manipulation before we can integrate. We need to find the integral of the quantity x minus 1 over x, all cubed. There is no power rule for integration of a function. We cannot simply integrate the inside and raise it to the power of 4. We must first expand the expression. We can use the binomial theorem or simply multiply it out. Expanding x1x cubed gives us x cubed minus 3x plus 3 over x minus 1 over x cubed. Now, let's rewrite the terms with negative exponents to prepare for the power rule. This becomes the integral of x cubed minus 3x plus 3x to the negative 1 minus x to the negative 3. Now we can integrate term by term. The integral of x cubed is x to the 4th over 4. The integral of 3x is 3x squared over 2. The integral of 3x to the negative 1 is 3 times the natural log of the absolute value of x. And the integral of negative x to the negative 3 is negative x to the negative 2 over negative 2. Finally, we simplify the expression. The two negatives cancel out, and x to the negative 2 becomes 1 over x squared. So our final answer is 1/4 x to the 4th. Minus 3 halves x squared plus 3 natural log of the absolute value of x plus 1 over 2x squared plus c. Let's look at another example that requires algebraic manipulation, this time involving division. We need to find the integral of the quantity 3 square root of x plus x squared, all divided by x. Just like with the previous example, there is no quotient rule for integration. We must simplify the expression first. We can do this by dividing each term in the numerator by the denominator, x. This gives us the integral of 3 square root of x over x plus x squared over x. Now let's simplify each term. We'll use exponent notation. The square root of x is x to the 1/2. So the first term is 3x to the 1/2 divided by x to the 1. Using exponent rules, this simplifies to 3x to the negative 1/2. The second term, x squared over x, simplifies to x. Now we have a simple polynomial-like expression that we can integrate term by term. The integral of 3x to the negative 1/2 is 3 times x to the 1/2 over 1/2. The integral of x is x squared over 2. And we add our constant of integration, c. Let's simplify the first term. Dividing by 1/2 is the same as multiplying by 2. So we have 3 times 2 times x to the 1/2, which is 6 times the square root of x. Our final answer is 6 square root of x plus 1/2 x squared plus c. This example highlights the importance of simplifying the integrand before attempting to integrate. Let's now look at a powerful technique for integration that comes directly from the product rule for differentiation. This is called integration by parts. The product rule states that the derivative of u times v is u times the derivative of v plus v times the derivative of u. If we integrate both sides with respect to x, we get the integral of the derivative of uv is just uv. On the right side, we can split the integral into two parts. Rearranging this equation to solve for the integral of u dv gives us the integration by parts formula. The integral of u dv equals u times v minus the integral of v du. This formula allows us to transform a difficult integral into a potentially easier one. The key to using this formula is choosing the right parts for u and dv. A common mnemonic to help with this is LIET. LIET stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. When choosing u, you should pick the function that appears first in this list. The remaining part of the integrand becomes dv. Let's see this in action with an example. Find the integral of x times cosine x. Using LIET, we have an algebraic term, SL, and a trigonometric term, TLISX. Since algebraic comes before trigonometric in LIET, we choose u equals x. So let u equal x and dv equal cosine x ds. Now we need to find du and v. The derivative of u is du equals dx. The integral of dv is v equals sine x. Now we plug these into the formula, u dv equal uv v du. This gives us x times sine x, minus the integral of sine x dx. The new integral sin x dx is much simpler. We know its integral is negative cosine x, so we have x and sine x minus negative cosine x plus c. Simplifying, our final answer is x sine x plus cosine x plus c. Integration by parts successfully transformed a product into a simpler integral. Let's try another integration by parts example, this time with a logarithmic function. Find the integral of the natural logarithm of x. This integral doesn't look like a product, but we can treat it as 1. ln x times 1. Using LIET, we have a logarithmic term, ln ax, and an algebraic term, g1. Logarithmic comes first, so we choose u equals ln x. Let u equal ln x and dv equal 1 dx. Now we find do and v. The derivative of u is do equals 1 over x dx. The integral of dv is v equals x. Now we apply the formula u dv u v v du. This gives us ln x times x minus the integral of x times 1 over x dx. Let's simplify the new integral. The x and 1 over x cancel out, leaving us with the integral of 1 dx. The integral of 1 is x. So we have x ln x minus x plus c. This is a very important result to remember. The integral of ln x is x ln x minus x plus c. This example shows how integration by parts can be used even when the integrand doesn't initially appear to be a product. Finally, let's look at a special case of integration by parts that leads to a cyclic integral. Consider the integral of e to the x times scenic. Using Liat, we have an exponential term and a trigonometric term. Exponential comes last, so we choose u equals sine x. Let u equal sine x and dv equal e to the x dx. Applying the formula, we get a to the x sine x minus the integral of e to the x cosine x dx. The new integral is not simpler. It's another product of an exponential and a trigonometric function. This is a sign that we need to apply integration by parts a second time. Let's focus on the new integral, e to the x cosine x dx. Again, we choose u equals cosine x. Applying the formula again, we get e to the x cosine x minus the integral of e to the x times negative sine x dx. Now, let's substitute this back into our original equation. We have the integral of e to the x sine x equals e to the x sine x minus the entire expression we just found. Notice that the original integral has reappeared on the right side. This is a cyclic integral. Let's call our integral I. So, I equals e to the x sine x minus e to the x cosine x minus I. Now we can solve for I algebraically. Add I to both sides to get 2I equals e to the x sin x minus e to the x cosine x. Then divide by 2. Finally, we add the constant of integration. The integral of e to the x sine x is 1/2 e to the x times the quantity sine x minus cosine x plus c. This technique is essential for integrals involving products of exponentials and trigonometric functions. Let's recap what we've learned today. We started with the fundamental idea that integration is the reverse of differentiation. We defined the indefinite integral as the antiderivative plus a constant of integration, c, which accounts for the family of functions with the same derivative. We then established key rules for integration, such as the constant multiple rule and the sum and difference rule, which allow us to integrate term by term. We built a table of basic integrals by reversing common differentiation rules, including the power rule, the integral of e to the x, the integral of 1 over x, and the integrals of sine and cosine. Finally, we explored two powerful techniques for more complex integrals: algebraic manipulation to simplify the integrand, and integration by parts, which uses the product rule in reverse to solve integrals of products of functions. You are now equipped to define and calculate indefinite integrals, understand the constant of integration, and apply these key rules and techniques to solve a variety of problems. The best way to master these concepts is through practice. To help you solidify your understanding, here are 5 practice questions in the style of IB mathematics analysis and approaches higher level. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Find the integral of 3x squared minus 4 over x plus 2e to the x. Question 2. Find the integral of the quantity x minus 2 times the quantity x squared plus 1. Question 3. Find the integral of sine of 2x plus 3. Question 4. Find the integral of x squared times the natural log of x. And question 5. Find the integral of e to the 2x times cosine of x. Take your time to solve these. Remember to show your steps and include the constant of integration. Welcome back. Let's go through the solutions together. Here's the solution to question 1. We integrate term by term. The integral of 3x squared is 3 times x cubed over 3, which simplifies to x cubed. The integral of negative 4 over x is negative 4 times the natural log of the absolute value of x. The integral of 2e to the x is 2e to the x. Adding the constant c, our final answer is x cubed minus 4, plus 2e to the x plus c. Now for question 2. First, we must expand the product. 2, x squared plus 1 equals x cubed plus x minus 2x squared minus 2. Rearranging the terms, we get x cubed minus 2x squared plus x minus 2. Now we integrate term by term. The integral is x to the 4th over 4 minus 2x cubed over 3 plus x squared over 2 minus 2x plus c. Here is the solution to question 3. This is a simple substitution. The integral of sine of ax plus b is negative 1 over a times cosine of ax plus b. Here a is 2. So the integral is negative 1/2 cosine of 2x plus 3 plus c. Let's look at question 4, which requires integration by parts. Using Lie 8, we choose u equals ln x and dv equals x squared dx. This gives us du equals 1 over x dx and v equals x cubed over 3. Applying the formula, we get x cubed over 3 times ln x minus the integral of x cubed over 3 times 1 over x dx. This simplifies to x cubed over 3 ln x minus 1/3 times the integral of x squared dx. The integral of x squared is x cubed over 3. So our final answer is x cubed over 3 ln x minus x cubed over 9 plus c. And finally, question 5, a cyclic integral. Let I be the integral. We choose u equals cosine x and dv equals e to the 2x dx. This gives us du equals negative sine x dx and v equals 1/2 e to the 2x. Applying the formula once gives us I equals 1/2 e to the 2x cosine x, plus 1/2 times the integral of e to the 2x sine x dx. We apply integration by parts again to the new integral, choosing u equals sine x. This gives us I equals 1/2 e to the 2x cosine x, plus 1/4 e to the 2x sine x, minus 1/4 I. Distributing the 1/2, we get I equals 1/2 e to the 2x cosine x, plus 1/4 e to the 2x sine x, minus 1/4 I. Adding 1/4 I to both sides gives 5/4 I equals 1/4 e to the 2x times the quantity 2 cosine x plus sine x. Multiplying by 4/5, we get I equals 1/5 e to the 2x times the quantity 2 cosine x plus sine x plus c. I hope these examples and practice questions have helped you understand the techniques of indefinite integration. Keep practicing, and you'll master this essential skill for your IB exams. Thank you for watching. Before we conclude, let's address a common question that arises from the power rule for integration. The power rule states that the integral of x to the power of n is x to the power of n plus 1 divided by n plus 1 plus c. But it explicitly states that n cannot be equal to negative 1. Let's see what happens if we try to apply the rule for n equals negative 1. If n were negative 1, the denominator would become negative 1 plus 1, which is 0. Division by 0 is undefined in mathematics. Therefore, the power rule simply does not work for this specific case. So what do we do when n is negative 1? We use the logarithm rule we discussed earlier. The integral of x to the negative 1, which is the same as the integral of 1 over x, is the natural logarithm of the absolute value of x plus c. This is a separate special rule that handles the case where the power rule fails. It's crucial to remember this distinction. Always check the value of n before applying the power rule. If n is negative 1, you must use the logarithm rule instead. Let's also clarify a point about the constant of integration, c, that often causes confusion. Consider the example we saw earlier. We found that the integral of 2 times the quantity 2x cubed plus 3x squared is x to the 4th plus 2x cubed plus c. We can also solve this by first pulling the constant 2 out of the integral. This gives us 2 times the integral of 2x cubed plus 3x squared. Now let's integrate the expression inside the brackets. The integral of 2x cubed is 2 times x to the 4th over 4, which is 1/2 x to the 4th. The integral of 3x squared is 3 times x cubed over 3, which is x cubed. So we have 2 times the quantity 1/2 x to the 4th plus x cubed, plus a constant, which we'll call c prime. Distributing the 2, we get x to the 4th plus 2x cubed plus 2c prime. Now compare this to our first answer. The variable parts are identical. The only difference is the constant term. In the first case, we have c. In the second case, we have 2c prime. Since c and c prime are both arbitrary constants, 2c prime is also just an arbitrary constant. We can simply rename it c. This is why we don't need to worry about constants multiplying the constant of integration. We can always absorb them into a single, new arbitrary constant c. Let's address one final point of potential confusion, this time involving inverse trigonometric functions. Consider the integral of -3 over the square root of 1 minus x squared. Tegan's answer was 3 arcos x plus c. Jill's answer was -3 arcs in x plus c. Which one is correct? Let's check both by differentiating. The derivative of arcs in x is 1 over the square root of 1 minus x squared. So the derivative of Jill's answer is -3 over the square root of 1 minus x squared. This matches the integrand. The derivative of arcos x is -1 over the square root of 1 minus x squared. So the derivative of Tegan's answer is 3 times -1 over the square root of 1 minus x squared, which is also -3 over the square root of 1 minus x squared. This also matches the integrand. So both answers are correct. This is because the derivative of arcs in x plus arc cos x is 0. This means arcs in x plus arc cos x is equal to a constant pi over 2. Therefore, -3 arcs in x plus c can be rewritten as -3 times the quantity pi over 2 minus arc cos x plus c. This simplifies to 3 arcos x minus 3 pi over 2 plus c. Since -3 pi over 2 plus c is just another arbitrary constant, we can call it c prime. So the two answers are equivalent. This demonstrates that there can be different yet equivalent forms for an indefinite integral. As long as your answer differentiates back to the original integrand, it is correct. Thank you for joining this video on indefinite integration. We've covered the fundamental concepts, rules, and techniques necessary for success in IB mathematics analysis and approaches higher level. Remember, the key to mastering integration is consistent practice. Work through the examples again, try the practice questions, and explore additional problems from your textbook or past papers. By understanding the relationship between differentiation and integration, and by applying the rules and techniques we've discussed, you will build a strong foundation for more advanced topics in calculus. Good luck with your studies.